Now this class is on the waves between parallel planes, about TM waves. That is, here we are going to see the various equations corresponding to the propagation of TM waves, that is transverse magnetic waves between parallel planes. So as a continuation of the last class, differentiation of equation 3b and substitution of the result and equation 3a into equation 3c will give an expression for magnetic field along y-axis, that is Hy, as this one. Okay, now if the space between parallel planes is considered a good dielectric or with properties mu1 and epsilon 1, provided sigma or conductivity very small, then in the above equation, dou square Hy by dou x square is maintained as such, whereas gamma square is also kept as such. Since sigma is small, we can neglect it, and the rest is replaced with the dielectric constant. So this equation will reduce to equation 6. Now the solution of equation 6 will be of this form, that is Hy is equal to a1 e raised to j root of gamma square plus omega square mu1 epsilon 1 x plus a2 epsilon raised to minus j root of gamma square plus omega square mu1 epsilon 1 x. Now a and 1 and a2, we all know they are arbitrary constants, and whose values are determined by the source of field excitation. Now the two exponential functions of x indicate the presence of an incident and reflected system for Hy, that is the two waves propagating in the plus and minus z directions, plus and minus x directions. Now the above equation, we can put it in a form in which it becomes easy to visualize. For that, we are using the expressions e raised to I theta. It is, we know it is cos theta plus j sin theta, and e raised to minus I theta is cos theta minus j sin theta. Then the above expression for Hy will reduce to this one, that is equation 7. Now by insertion of this equation 7 in equation 3a, the value of electric field component along z axis, that is epsilon z, can be obtained as equation as that given by equation 8. Now this component epsilon z can also be obtained from equation 3b as follows, and that is given by equation 9. So this equation, I think no need of, you can skip this equation, no need of mentioning this. You can just stop writing at equation number 8, and after that you can write the explanation for this. Okay, that is, for each of the fields, it is clear that the value along x-axis is a resultant of two fields traveling in opposite direction, and it is because of the lack of attenuation in this direction a true standing wave pattern is developed. Now in order to determine the value of the arbitrary constants b1 and b2, we have to consider that the planes that we are considering is a perfect conductor. That is, to find the values of arbitrary constants b1 and b2, we are just assuming that the plane along which the waves travel are perfectly conducting, and at the extreme end of the plates, that is at x equal to a by 2 and x equal to minus a by 2, the tangential component of electric field is assumed to be 0. And on examining this particular equation 9, so since we are skipping equation 9, we can refer to equation 8 and say that the value that is obtained that particular value will be obtained either if the constants b1 equal to b2 equal to 0, or the angle is of the value or the angle must have integral multiple of pi by 2, especially at a by 2 and minus a by 2. So here up to equation 8 you have to write, and then after writing equation 8, no need of writing this equation, just write the explanation here. That is that equation actually represents that of a standing wave pattern, and then next aim is to find the value of the arbitrary constants b1 and b2. For that we are making an assumption that the planes along which the waves travel are said to be a perfect conductor, and at the extreme end of the plates, that is x equal to a by 2 and x equal to minus a by 2, tangential component of electric field is supposed to be 0, and if that is the case, then b1 and b2 in equation 8 must be 0, or the angle between them must be an integral multiple of pi by 2 at a by 2 and minus a by 2. Okay, now on making such assumptions, accordingly it can be said that boundary conditions require a particular equation like this. So from this you have to find this particular value. On rearranging this 2 and 2 will cancel, so m pi by a, where m is equal to 0, 1, 2, 3. Then we can also write the z component of electric field as given by equation 11. Now when the field is examined at planes within the limit x equal to a by 2 or x equal to minus a by 2, three possible conditions lead to zero field intensity, and those conditions are as follows. That is, if m is equal to 0, then epsilon is equal to 0 everywhere. If m is even, then b1 equal to 0. If m is odd, then b2 is equal to 0. Now the configuration of field between the planes depends on the value of the integer m, and we can designate the wave as per the value of m. That is, for m equal to 0 we call it as tm0 wave, for m equal to 1 we call it as tm1 wave, for m equal to 2 we call it as tm2 wave. So depending upon the value of m, we can designate the wave. These various configurations of field intensity in the guide are called modes of propagation. Now this distribution can be either sinusoidal or cosinusoidal in the x direction. Now the number of maxima depends on the value of m. Now here we have discussed about the propagation of wave in the positive z direction only. That is why we are writing epsilon raised to minus gamma z. Now this constant is actually a complex one, and so we have to express it in terms of attenuation constant alpha and phase constant beta. So that constant or the complex constant gamma is expressed as the sum of the attenuation constant alpha and phase constant beta as follows. Now the value of gamma for a particular field is written of the form given by equation 12. The value of gamma will be either real or imaginary. So there are two conditions, that is, gamma can be either real or imaginary. So thus two conditions arise. Now with alpha equal to 0 or with beta equal to 0. Okay, so since gamma can be either real or imaginary, there will be two conditions arising out of that. One is alpha, attenuation constant, will be 0, or phase constant beta will be equal to 0. It is possible to have propagation with 0 attenuation or high attenuation with beta equal to 0. The angular velocity omega or frequency is a factor determining whether or not propagation takes place for a given spacing a of the planes. Now the critical frequency fc at which attenuation condition changes to the propagation condition is determined from the equation. So this equation 13 is the expression for critical frequency. In terms of critical frequency, we can write the value of m by a as follows, or in terms of critical frequency and the integer m, the complex constant, that is gamma, can be represented as equation 14 or by equation 15. It is better you can write only equation 15. Then we can write two conditions. One is for frequencies below cutoff and gamma is real. What happens to the field? The field are attenuated and the complex constant gamma will be having only the attenuation constant because the wave is attenuated, whereas the phase constant beta will be 0. The phase angles will be constant and the field amplitudes will decrease very rapidly with the distance z. Then what happens if frequency is above cutoff? Then that complex constant is imaginary, attenuation constant is 0 and the propagation will occur, and the expression for that complex constant gamma m is given by equation 70. Now what we are interested is the direction in which no attenuation occurs. Okay, in practical case, because of the finite conductivity of the plates that we are considering, anyway some attenuation will occur during the propagation of the wave, and that occurs especially at frequencies above cutoff. The action of plane in only propagating frequencies above cutoff will have a close resemblance to the operation of a high pass filter. This similarity has led to many study of relations for cutoff, then study of attenuation, etc. Here they have given one more expression for the critical frequency. Fc is equal to V1 by 2A by m, and the expression for critical wavelength is given as lambda c is equal to 2A by m. Then they also have given the expression for critical wavelength as it is the relation of critical wavelength to the plate spacing A as m lambda c by 2 is equal to A. So three expressions they have given, one for critical frequency, critical wavelength, and the relation between critical wavelength and plate spacing. So that the critical wavelength is fixed as that at which the distance between plates become exactly m half waves. For long waves, that is for longer wavelength but low frequency, the plane will serve to attenuate the fields, that is the fields will get attenuated, whereas for short waves or long frequencies will be propagated between the plates without any loss. The integer m can thus be interpreted as a number of field maximums occurring in x direction between the planes. So the three field components can be written by including the time and z propagation, and those three field components, that is hy, epsilon z and epsilon x, are given by equation 19, 20 and 21. These are the three expressions or the equations for TM waves that we have considered. Now this particular form is obtained by the use of the value for gamma equal to j beta m in the propagation region and consideration of the meaning of j coefficient appearing before magnitude function in some cases. So no need of writing all that, you just write that these are the three expressions that we derive for the propagation of TM wave between parallel planes, or the equations 19, 20 and 21 represent the propagation of, or they actually stands for the relation that gives the propagation of TM waves between parallel planes. Okay, thank you.